Okay, so I went ahead and I continued on with lecture, not knowing that it had run out of time. I was getting carried away with our ozone creation and how it's formed. So I'm just going to go ahead and go through this one diagram. So keep in mind that ozone is made up, it's O3, okay, so 3 oxygen atoms. Now, we know that ultraviolet light can break up an oxygen molecule, allowing for free oxygen atoms to join with O2, okay, so additional oxygen. So forming the O3. Now, we know that the ozone is in the stratosphere. We know that the ozone is a filter that helps protect from this ultraviolet light. And ozone can cause skin cancer, it can cause cellular mutation, and that, so these harmful rays need ozone to filter through to protect us. Now, there are periods of times when we have low pressure systems that come through an area, and ozone from the stratosphere can be measured at the surface. Okay, and so when that takes place, we see that there's high levels of ozone at the surface, and ozone can cause for respiration issues, irritation, and so we monitor ozone when there's a low pressure system going through a particular area. Now, how can the ozone layer become depleted? Now, we talked about CFCs, and CFC molecules, chlorofluorocarbons, are released through coolants, refrigerators, air conditions. Remember, they were banned with the Montreal Protocol back in 1987. Now, the chlorofluorocarbons are very light, and they make it up to the stratosphere. And these chlorofluorocarbons, when they react to ultraviolet light and can become separated from the chlorine. So ultraviolet light will split up the CFCs and provide a chlorine atom to become free range, and that chlorine atom can combine to a oxygen molecule and break up our O3. Okay, so literally it's the division of the chlorofluorocarbons that break up our O3, and that is the depletion of the ozone. So you can walk through this cycle. Now, we identified where these depletions take place, and we see that this kind of a seasonal change, ebb and flow of the ozone hole. We can map out where the hole is. We see that during the summer months in Antarctica, we see that the hole can grow. It also can cover areas of Australia and New Zealand. And we can see that when we map the hole itself, we can see certain areas where there are larger amounts of ultraviolet light making its way to the Earth's surface, so we can actually map out this ozone hole depletion. So what I want you to take home is that ozone is important, O3. Know the process of O2 combining with an oxygen molecule to create O3. It's a natural cycle. So the ozone layer is very important. And how the ozone layer becomes depleted is when we have chemicals and elements such as the chlorofluorocarbons, CFCs, that are broken up by the UV radiation and provides a free radical chlorine that can break up our O3. Okay, so let's go ahead now and put our stratosphere on our chart here. So the stratosphere is higher. It sits upon the tropopause. We see that as we increase now, because we have the ozone in the stratosphere, we have a temperature change. So now we're seeing some thermal changes within the stratosphere. And then upon the stratosphere, we have the stratopause. So take-home message is that this is the layer that ozone exists. Okay, the second layer is the mesosphere. This is described as the middle sphere. And this layer is the layer of decreasing temperature. So it's one of the coldest layers in our atmosphere, and we identify the mesosphere at 50 to 80 kilometers above the Earth's surface. Now, mesosphere, looking at our thermal charts here, it's the coldest. So here, what we're experiencing here is now we're so far removed from the Earth's temperature. So therefore, the thermal mechanism for heating up the mesosphere really doesn't exist at this point. It's obsolete. We're not getting energy from the Earth's surface. So it's a very, very cold layer. We also have the mesopods. Okay. Now, when we look at the mesosphere, we know that it's the lowest temperature in the atmosphere because we're so far removed from the Earth's surface of that re-radiating energy. And then we go ahead and talk about the upper layer of the atmosphere identified as the thermosphere. Okay, thermosphere meaning heat. Okay, so this is going to be one of the hottest layers because it's thinnest, it's closest to the sun. So we see that there's kinetic energy here, energy in motion, and we can measure that energy in the form of the thermosphere. So in adding the thermosphere's property to our chart, it's going to be the hottest layer. So you should be able to identify key components that exist in the troposphere, stratosphere, mesosphere, and thermosphere for this class. We can also identify that the thermosphere exists at 80 to 480 kilometers above the Earth's surface. This is going to be the layer of the atmosphere that is going to be bombarded by those shortwave radiations from the sun. It's going to have the highest temperature. And so as we go ahead and look back at this cross-section of the Earth's atmosphere, we see that we have the thermosphere identified as the outer edge of the atmosphere. Okay, temperature and heat are different concepts when we talk about the Earth's atmosphere. When we talk about heat, the actual flow of energy from one molecule to the next, or from one surface to the next. When we talk about temperature, we're talking about kinetic energy, so vibrating molecules. Okay. And when we talk about the troposphere having a lot of the molecules, heavier molecules, they can collide with each other because there's quite a few of them, since 90% of the atmosphere exists closest to the Earth's surface. And the further you go out, you have less molecules. So, for example, molecules in the thermosphere may move a half a mile before actually colliding with one another. So very little molecules out there. We can go ahead and apply the same temperature cross-section and identify key components within the atmosphere. So looking at temperature on our x-axis and altitude on our y, and see how that temperature fluctuates. So hopefully you guys are catching on that I'm emphasizing a lot of time and slides to talk about the changes in our atmosphere, the thermal properties and characteristics. So you should be able to know this. All right, so we're going to go ahead and shift gears here and talk about latitude and temperature. Now, one thing that we see here on this chart is as we move up in latitude, we see fluctuations in temperature. So we're looking at this climate chart, looking at the months of the year on our x-axis, so January, February, March, April, May, and so on and so forth. And then looking at latitude. So we're going from high latitude to 71 degrees north, of representing Barrow, Alaska, to 13 degrees south in Brazil. And we see that we have some very interesting seasonal fluctuations in temperature. And we also see we have some very interesting characteristics with latitude, and even looking at elevation, how that influences. But one thing that we also see is that we have this great seasonal pattern that we see here. So looking at the temperature for Barrow, Alaska, the temperature is going to be the highest during the summer months. But looking at Brazil, where it's at 13 degrees south at an elevation of 9 meters, look how there's very little fluctuation here. Okay, it's very constant. Now, I'll make you a bet that this location right here is close to the ocean as well. And so 9 meters is not very high. And notice that it's just a very consistent temperature line across the months. So 13 degrees south is along our area of energy from our subsolar point. So very little seasonality here, very little fluctuation in temperature versus our pretty extreme fluctuation here of Barrow, Alaska. So when we go and start talking about global temperature and land water heating principles, we need to identify elements that are going to influence temperature change. So latitude is going to be a huge influence. Temperature controls, land water heating differences. So if you're close to land or if you are more continental, so marine versus continental is going to influence temperature. And then also other temperature patterns that we see. So vegetation is going to have a huge concept. So when we start talking about temperature concepts, okay, this is a bit of a review here. Remember that sensible heat is something we feel versus temperature, which is kinetic energy of molecules. So we feel heat when kinetic energy is transferred from molecules to us. And so remember that the measurement of temperature, we identify it's in degrees Celsius, Fahrenheit, or Kelvin. So three different ways that we can identify and measure temperature. So when we're looking at latitude, okay, we're looking at our incoming energy from the sun, knowing and identifying where we have the surplus of energy along between 23.5 degrees north and 23.5 degrees south. Okay, this is where we have a surplus versus our deficit. Okay, so the insolation decreases as we move away from the subsolar point. And we also see that we have a cyclical cycle with changes in day length and the sun angle with increasing latitude. Okay, so latitude is a key component. So we're going to come back to this chart now. Now, as we increase in latitude, going from 30 degrees north to 70 degrees north, we have these extremes that take place here. So latitude is going to have a huge influence on temperature in a particular location. Altitude is another major factor. So temperature decreases in the troposphere at a lapse rate. And we identified that lapse rate as being 6.4 degrees Celsius for every 1,000 meters. Okay, there's a range there. We'll talk about that range later. Now we also see that the atmospheric density decreases in elevation. So as you get higher and higher, you have less air, okay, less molecules. A thinner atmosphere can absorb less energy, therefore temperature drops with altitude. And atmospheric density at 5,500 meters is half of what we'd see at sea level. So that makes sense. When you're climbing at higher elevations, there's less oxygen for you, less molecules. And we can see that when we look at two locations, comparing La Paz, Bolivia to Concepcion, we notice that we have a change in altitude. So Concepcion's in red and La Paz is in blue. La Paz, Bolivia is at 13,000 feet and Concepcion is about at 1,600 feet. Okay, they're both at the same latitude, but we see that there's a change in elevation. And we see that there's La Paz, we see are much cooler temperatures versus Concepcion. When we go ahead and talk about marine locations versus continental, marine meaning that you live by the ocean. Now, marine, being by the ocean, remember we said that the ocean regulates the release of energy. And so looking at this particular location through the calendar months of the year, we can see that we have very little fluctuation versus a location such as Barrow, Alaska, or let's say North Dakota, where you are away from a water body, but you're experiencing these extreme fluctuations here because we don't have the ocean to regulate the temperature. So the two examples that we're looking at here is we're looking at Wichita, Kansas, okay, which is in the middle of the United States, so continental, versus San Francisco, okay, versus has more of that marine influence, its location is closer to the ocean that allows for temperature to become regulated. And as a result, we see that we have very little fluctuation in the temperature range versus very extreme hot summers, very cold winters. I'm going to go ahead and stop there and we'll continue our lecture in the next half.